Hi, and welcome to Mathematics for Machine Learning. So in the last lecture, we have shown Taylor's theorem. Today we will use this theorem to prove some properties of optima of high-dimensional optimization problems. We will focus on minima, but of course without loss of generalization, you can apply the same rules also to maxima. Just, whenever we talk about positive definite, replace that with negative definite, and positive semi-definite, replace it with negative semi-definite, and so on and so forth. So let's review Taylor's theorem. Suppose our function f, which goes from r to the d, so it's a high-dimensional function, is continuously differentiable, and we have our displacement vector h. Then there exists a scalar t that is in the interval between 0 and 1. We don't know what it is, but we know that it exists, such that f of x plus h, so f at x displaced by h, equals to f of x plus a term that is linear in the gradient of f at this point x plus the scalar t times h transpose times h. So what does this mean again? Well, the function value at x displaced by the vector h is equal to f of x plus, and here we have not f of x plus h, but f of x plus th, so this little scalar between 0 and 1. So this yields a point that lies between x and x plus h. So if we have our point x here, and we have our point x plus h, where this would then be the vector h, then x plus t times h, so we're multiplying h by a scalar that is between 0 and 1, will lead to some vector here on this line. Furthermore, if f is twice differentiable, then the gradient of f at this point x plus h, so at the point here, can be given by the gradient of f at the point x. So this tells us a little bit about how the gradient changes, plus the integral from 0 to 1 of the Hessian matrix. So it's the matrix of all the second partial derivatives of f at x plus t, that's the scalar that we're integrating over, times h. So that means we're integrating basically over all the points that lie between x and x plus h, times the vector h. So the result of this matrix vector multiply yields again a vector. In addition to the gradient, we can also write f itself at the point x plus h as the sum of f of x, then a linear term in the gradient, plus a quadratic form in the Hessian. So the gradient times this displacement vector h and the quadratic form in the Hessian, but the Hessian at this point t times h, where again we don't know which of these points it is, we only know that it exists. So how is this useful? Well, that we will see today, because we will use these three expressions to prove various things about optima of high-dimensional optimization problems. The first thing is that if we have our function f, which takes a vector x as input, and we have a point x star that is a local minimum of this function. Of course, remember, we can say the same things about local optima. And if f is continuously differentiable in a neighborhood of x star, so that means that if we take x star and move a little bit around from it, it's still differentiable, then the gradient of f at this point x star equals to 0. So something that we intuitively should already know. If you remember from school, then the derivative at the maximum or at the minimum of a function is 0 if the function is differentiable. And here in the high dimensional setting, not the derivative is 0, but all the partial derivatives are 0, meaning that the gradient vector equals to 0. Now let's prove that by something that leads to a contradiction, namely the following statement. So let x star be such a local minimum of f. And now suppose that the gradient of f at this x star is not equal to 0. So just the opposite of our proposition. And we'll go through a number of steps and see that if we assume that the gradient at this minimum is not 0, then turns out that the point x star is actually not a minimum. So, but how do we get there? Well, the first thing that we do is we define our vector h to be equal to the negative gradient of f at this point x star, at this local minimum. From that, the following follows. So if we look at minus the gradient of f at x star plus a constant t times h, and let this t go to 0 by taking the limit of t going to 0, then the result of this limit should be the negative gradient of f at the point x star, because this term here goes to 0. Thus, this is nothing else than our chosen h. In the next step, let's multiply h to the gradient of f at x star plus, again, a small constant t times h. And let's look at how this product of these two vectors, so the vector h and the gradient vector at x star plus th looks in the limit. So again, we let t go to 0, which means that this term here goes to 0, and we're left with the gradient of f at the point x star times h as the limit of that. Now by the choice of our h, if we plug it in, we have now here minus the gradient of f at this point x star times the gradient of f at the point x star. So it's minus the dot product of the gradient with itself, which is equal to the squared L2 norm of h. Because we have minus times minus, so let me write this out. Minus gradient of f at x star transpose, that's our h, times the gradient of f at x star, which is minus h, but of course we can now negate this term and put the minus in front, which means we have minus h transpose h, which is the same thing as saying that this is the minus the squared L2 norm of h. But what we have here is now the vector h multiplied with itself, so this is always positive, times a minus in front, so the result will be always negative. Unless h is equal to 0. But we have assumed that the gradient of f at this point x star is not equal to 0. Thus, h is also non-zero. So this has to be negative here. So what we have now shown is that the product of h times the gradient of f of x star plus a t times h is smaller than 0 if we let t go towards 0. That means that somehow there needs to be a very small t where this holds, that the product of h and this gradient at this point x star plus th is smaller than 0. Thus, there should be an upper bound capital T such that for all t that are between 0 would have just the limit here, and this upper bound t, the last statement holds. So there exists a capital T, this is this upper bound, such that for all little t in the interval between 0 and this upper bound capital T, the product of h and the gradient of f at x star plus th is smaller than 0. Now for all of these little t's, let's look at the function value at x star plus this little t times h. Of course, on this point, which is x star plus th, we can apply Taylor's theorem. So we have our point x star, our optimum, then we have our point x star plus th, and we know that this should be a minimum, and we're now interested in the function value at this point here. So x star displaced by t times h. And of course we can apply Taylor's theorem to look at this. So this should be equal to f of x star plus a linear term. The displacement vector is now not h, but it's t times h. So we have our little t here. Transpose times the gradient of f at x star plus a new point t prime h, where t prime is smaller than little t. So it's in the interval between 0 and t. So this gives us a vector that lies at the line between x star. So this would be our point x star plus t prime times h over here, yeah? Now this term just follows from applying Taylor's theorem, but because t prime also lies in this interval between 0 and capital T, because it's smaller or equal to little t, we also know that it also has to yield a value smaller than 0 for the product of h with the gradient of f at x star plus this t prime of h, because it's smaller than t and it holds for all the points in this interval. So this is smaller than 0, which also means that if we multiply it again by t, is still smaller than 0. So what we have just shown is that f of x star plus th equals to f of x star plus something that is smaller than 0. We get a value that is smaller than f of x star, which means that f of x star plus th has a smaller function value than our minimum, which in turn means that, well, x star cannot be a local minimum. So that gives us our contradiction, which means that this statement obviously cannot hold. Thus, the gradient of f at this point x star needs to be 0. So this proof shows very nicely why a gradient of f at an optimum needs to be 0. So it needs to vanish in order for x to be an optimum. Namely, if the gradient is non-zero, as we have just assumed in our proof, then we can always find a tiny step in the direction of the negative gradient. So we can always take the gradient, multiply it by a very small step alpha, and go a little bit in the opposite direction. So subtract that from x in order to decrease the function value. It also means that the negative gradient is a descent direction, because if we make a tiny alpha step in this direction, our function goes down. And the only way that this gradient or the negative gradient is not a descent direction is if the gradient is 0, because then this term would also yield 0, so we would not move anymore using this descent. These points where the gradient vanishes are called stationary points. However, not all the stationary points are extrema, so they're not all maxima or minima. Let's look at an example, namely a two-dimensional function. So it's a function that has x and y as inputs, and it computes the difference in x squared and y squared. So x squared minus y squared is our function. So it's a function that takes an input from r squared and outputs a scalar value r. Now let's look at the graph of this function. Here we see our x dimension. Here we see our y dimension. And here we have the point 0, 0. And you see that this point 0, 0, where the gradient is equal to 0, somehow is a minimum along the y dimension, because there along the y dimension, if we move away from this point 0, 0, it goes down in this direction and it goes down in the other direction. And if we look at the x dimension, it goes up here and it goes up here. So if we're just moving along this axis, keeping y always 0, so we're moving just in this direction, it is a minimum because we would go up here or here. And if we keep x equal to 0, we would be moving on this line here, it would be a maximum. But if we move in 2 dimensions, it would be neither a minimum or maximum. It's only a minimum maximum if we look at along one line, not along all the dimensions of this problems. And these points that have a zero gradient, so where the gradient vanishes, nothing else than saying gradient f equals 0, but they are not a minimum or maximum, so they're not an extremum locally. They're called saddle points. And why are they called saddle points? Well, if you look at this graph, it very much looks like a saddle. So you can imagine a cowboy sitting in this saddle here, yeah, and riding a horse. So what we have just seen is that just saying that the gradient equals to 0 is not enough to say that we have an extremum. So they're not sufficient to characterize local minima or maxima. However, what can we do if we add second order information, namely the Hessian matrix? Well, let's look at it and prove the following proposition. We will prove a necessary second order condition for a local optimum, in particular a local minimum. So if x star is a local minimum of f, and f is now twice continuously differentiable around this point x star, so in the neighborhood of x star, then the Hessian matrix is positive definite. Or different way to write this is the Hessian matrix is positive definite. So it's this wavy larger or equal to sign than 0. We will again prove this by making a statement that leads to a contradiction. So we will say that the gradient equals 0, but the Hessian is not positive semi-definite. So let's see what happens. So let the point x star be a local minimum of a function f, and suppose that the Hessian is not positive semi-definite. So we take our positive semi-definite sign and we cross it through. Doesn't hold. Yeah? Now we choose our h such that the squared form in the Hessian is smaller than 0, which we can do because it's not positive semi-definite. If it was positive semi-definite, there would not be such an h. But because we are saying it doesn't hold, we can find one. Yeah? And that's what we work with. Now we look at the Hessian at f of x star plus a constant t times h. So we are going from x star to x star plus h to some point between that, and take the limit on this line going to 0. And of course the limit of the sum, because this will go to 0, will then be the Hessian of f at our minimum x star. It also follows that if we actually look at this squared form here and replace in the squared form the Hessian of f at x star with x star plus th, and instead of taking the squared form in the Hessian at the point x star, we're taking the Hessian at the point x star plus th and let the limit again go to 0. It follows that if we plug in this form here, this is of course also smaller than 0 because we chose our h exactly in that way, such that the squared form equals to a value smaller than 0. And because we took this limit going to a value t, letting this value go to 0, there needs to be some upper bound to those values of t where the whole interval between the upper bound and 0, that the squared form is already smaller than 0. And that we can do because of the continuity of the Hessian. We will, similarly to before, now once we are in this interval, apply to any of these points Taylor's theorem, which means that we can find between, here we have x star, here we have our x star plus th, and we now move on this interval by looking for x star plus t prime h for some point in between where the equality of f x star plus th, so the function value at x star that is located by th, equals to f of x star plus t times h transpose the gradient of f at x star plus 1/2 times the squared form in th, so we get a t squared here, and instead of having a squared form in th, we can write it as a squared form in h of the Hessian at this point t prime times h. And of course, we just showed that this value for all the t's in the interval between 0 and capital T has to be smaller than 0. So it also has to be the case for t prime, which also is in this interval. So this term is smaller than 0. We said that we have a local minimum, so the gradient equals to 0, as we have just proven in our last theorem. So we're taking a point f of x star, we're adding 0, and then we're adding a term that is smaller than 0. So again, our function value at x star plus th is smaller than the function at our optimum x star, which again is a contradiction because it would mean that x star is not a local minimum. Thus, the Hessian of f at this minimum needs to be positive, semi-definite, as we wanted to prove. In the last two theorems, we have proven two necessary conditions of local minima. Those are conditions that if we know that the point x star is the local minima of a function, then the first order condition needs to hold, namely the gradient needs to be 0, and if it's twice differentiable, also the second order condition has to hold, namely that the Hessian at this point x star is positive semi-definite. However, we cannot from this first order conditions say the reverse. So say we have a point where the gradient is 0 and the Hessian is positive semi-definite. That alone is not yet enough to say that the point is a local minimum. So the goal of the sufficient conditions is to take this reverse. Suppose f is twice continuously differentiable with the Hessian at this of the function f being positive semi-definite in a neighborhood of some point x star. So we are starting out with some point x star. We don't know whether that's a minimum or not, but we do know that the gradient of f at point x star is 0, and that the Hessian is positive semi-definite. But not only at this point x star, but also in a neighborhood around x star. So if this is our neighborhood, then in any point here, here, we would get a positive semi-definite Hessian. So not only at the point, that would be our necessary condition. If we had a minimum, then we would know that at this minimum, the Hessian is positive semi-definite, but rather we say that we have a point where the gradient is equal to 0, and at this point and in the neighborhood around this point, the Hessian is positive semi-definite. Then we can do the reverse and say, then x star is a local minimum of the function f. So how do we prove this? This time we won't prove by contradiction, but rather start out with a ball around this point x star. So starting out with a ball B that is centered at x star, and it has a radius of r. Now, of course, for any point within this ball, the Hessian needs to be positive semi-definite. So we can now write any point within this ball as the sum of x star plus the displacement vector h, where the displacement vector has a norm smaller than r. So as long as we don't go more than r away from x star, or because it's an open ball, as long as we go less than r away from x, we know that the Hessian needs to be positive semi-definite because we're still in the ball which is contained in our neighborhood. Now let's look at Taylor's theorem to look at the function value at this point x star plus h. So that's any point within the ball. This can be given by the function value of f at x star, which we don't know, plus the gradient of f at the point x star times h. And because we know that the gradient is 0, this term also needs to be 0, plus a squared form of this displacement vector h in the Hessian at some point that lies between our point x star, the center of the ball, and x star plus h, this other point that we want to go to. And that we do by saying that there exists, well, Taylor's theorem, some scalar t between 0 and 1, such that x star plus th fulfills this property that we can write the function at x star plus h as the sum of these terms. Now, because x star plus h lies within this ball, it also is clear that x star plus t times h, which is even closer to x star, has a positive semi-definite Hessian. So this squared form here is larger or equal to 0 because of this positive semi-definiteness, which means that the function value at x star plus h is larger or equal to the function value at x star, because we started out with f of x star plus 0 plus a term that is larger or equal to 0. So we cannot get smaller, we can only get larger. And this holds because we know that the point x star plus th will lie in the neighborhood where the Hessian is positive semi-definite. Thus, the squared form in this Hessian will be larger or equal to 0. Now, because f of x star is smaller or equal to f of x star plus h, see, f of x star plus h is larger or equal to f of x star. So the other way around, we know that f of x star is smaller or equal to f of x star plus h for any h within this ball. So for any directions where the radius of the ball is larger than the norm of h. So no matter where we go in this ball, we get that f of x star is smaller or equal to f of x star plus h. Thus, x star is a local minimum. So let's make the sufficient condition even stronger. Suppose that f is again twice continuously differentiable with a Hessian that is positive definite at our point x star, and again positive semi-definite in a neighborhood around x star, and that again the gradient of f at the point x star is 0, then x star is a strict local minimum of f. So again, we have a point x star with a Hessian at f x star that is positive definite. So this is this curly larger than sign, and in a neighborhood around this point x star, for any point here, the Hessian would be positive semi-definite. Then x star is a strict local minimum of f. Assume that the Hessian of f at x star is strictly positive definite. Since the Hessian is continuous, we can choose a ball B prime with a radius r prime larger than 0 that is centered around x star, such that for all of the points in the ball, the Hessian is positive definite. So for any point, the radius r prime, the Hessian of f at x star plus h, where h now has a norm that is smaller than r prime, the Hessian is also positive definite. So why do we know that the Hessian at the point x star is positive definite? Implies that it also has to be positive definite in a ball around this point x star. That is because the Hessian is continuous. So we said that it's twice continuously differentiable. So the Hessian is a continuous function. There's no jumps. All the eigenvalues of the Hessian are positive. And now we are continuously, infinitesimally, we can move away from this point and still have points where all the eigenvalues are positive. So this ball doesn't need to be closed, it can be open, but it needs to exist and has a radius that is larger than 0. So some points around this point x star still has to have a positive definite Hessian. So the Hessian, the eigenvalues don't jump, they can slowly decrease and then go towards 0, but they cannot jump. So let's use Taylor's theorem to look at the function value of a point that lies within this ball B prime. So we express this point within this ball as the sum of x star plus this direction h, which can be any vector that has a norm smaller than r prime, the radius of the ball, such that we're not moving outside here. This function value equals to the function value at the point x star plus a term that is linear in the gradient of x star, which is 0 because the gradient is 0, plus a squared form in the Hessian at some point between x star plus h and x star. So it's that we get from Taylor's theorem. So we know that it exists, but we don't know which it is. But of course, this is still in the ball. It's actually closer to x star. So the Hessian again has to be positive definite at this point x star plus th. Thus, the squared form needs to be positive. So what we have done is we've computed f of x star plus 0 plus a value that is larger than 0, means that the function value at x star plus h is larger than f of x star. Thus, x star is a strict local minimum of the function. What does it mean? It means that if we move away from this point x star, the function increases no matter how little we move away. So if this is our function, we are here, we're just going tiny bit away from here, the function value increases. There are no flat regions down here. Remember, as we said before, the necessary conditions alone are not sufficient. So if we just know that the gradient at a point x star is equal to 0, so the gradient vanishes, and that the Hessian is positive semi-definite at this point, we cannot yet conclude that we have a local minimum at x star. For example, let's look at the function f of x equals x cubed. We have a first derivative, so the gradient would be the vector of all the first partial derivatives, so the gradient of f at x star is a vector that has this one single derivative in it. So the gradient is equal to 0, and the Hessian is also equal to a matrix that is a 0, namely this matrix of the second derivative. It's 0, so the Hessian is positive semi-definite. Now let's look at the function. Here we have our point 0. And we see that here we have a derivative that's equal to 0, so the gradient is equal to 0 as well. And the Hessian that is 0, so 0 is positive semi-definite, but the point is a saddle point. It's neither a maximum nor a minimum. Let's look at the second example that is a little bit more nasty even. Here we have the function minus x to the power of 4. It looks very similar to a parabola, but is a little bit more flat here around this point 0. Now, the first derivative at 0 is equal to 0, and the second derivative is also equal to 0, which means that the Hessian matrix is positive semi-definite. However, here we actually have a strict local maximum of the function. So even if we go a tiny bit away from this point 0, the function value will decrease. So we have a strict local maximum. So what this also shows us is a counterexample for the reverse of our sufficient condition, the second sufficient condition. So if we just say that we have a point that is a strict local maximum, it does not apply that the Hessian is positive definite. Thus, we need to say that the Hessian is positive semi-definite around the point x star, so in an area around. That's our first sufficient condition. Now the problem is, how do we verify that the Hessian is positive semi-definite not only at a single point but at an area? That's usually not very easy. Well, sometimes you can vary this analytically. It's certainly not easy to do computationally, because you would have to basically try out any point around it, but in a continuous space that's not very practical. But sometimes we can do this analytically for some regions. For example, typical proof would just show it for the region of all of RD, that the Hessian is positive semi-definite. Then certainly you know that any point where we have a 0 gradient would be a minimum. Or if the Hessian is strictly positive definite and the function is twice continuously differentiable, then the continuity assumption of f applies also, that the Hessian around this point is positive semi-definite, or even positive definite in area around the point x star. So let's summarize. We have reviewed Taylor's theorem again and have used it to prove the necessary conditions of local optima, which are that for a function that has an optimum x star, the gradient at this point x star is equal to 0, and if the function is twice differentiable, then the Hessian at this point x star is also equal to a positive semi-definite matrix. Second, we have said that the necessary conditions are yet not sufficient to go the other way. So we have introduced the sufficient conditions, namely that if we know for a point that the gradient equals to 0 and the Hessian is positive semi-definite at the point and in a neighborhood around this point, then this point needs to be a local optimum. And if the Hessian is even positive definite and the second derivative is continuous, then the point is even a strict local optimum. And with this, I want to say thank you and see you next time. Bye bye.